Hi there. Today we're looking at a bio-inspired bistable recurrent cell allows for long-lasting memory by Nicolas Vecovin, Damien Ernst, and Guillaume Drian of the University of Liège. This paper here is not a paper that wants to push state-of-the-art on anything. It is a paper that takes a concept from the biological research on actual neurons, which is the bistability property, and tries to introduce it to recurrent neural networks. And on toy data or small data, they show that this has the interesting property that these recurrent neural networks can then remember important things for much, much longer than our current recurrent architectures can do. I believe this is a very interesting paper, and it's a nice, refresher from the whole state-of-the-art number pushing papers. So dive in with me to explore this. If you like content like this, also consider subscribing if you aren't, and sharing it out, and leaving a like and a comment if you have any sort of comments. All right, they basically say recurrent neural networks provide state-of-the-art performance in a wide variety of tasks that require memory, which is true, right? So we have these recurrent neural networks, and what the recurrent neural networks do is they're basically, so a classic recurrent neural network goes something like this. There is a hidden state at time step t, and there is a sequence of inputs that you have to work with. So we'll call them x1, x2, x3, x4, and so on. And then at some point you have to provide an output. This could be at every single time step, or sometimes it's just at the end you have to provide an output y. So for example, this here could be a piece of text, and you need to decide whether or not that piece of text, maybe it's an email, whether or not that's spam. This could be a time series of a patient in an ICU, and you need to decide whether or not to give some medication to the patient. So the applications of this are very wide, and any sort of series data will do. So there's this hidden state, and at each time step, this hidden state is updated to a new hidden state. So call this H0. It's updated to a new hidden state by incorporating the input. So somehow the input X and the previous hidden state are made into a new hidden state. And then the next input is taken in, and by using this hidden state, a new hidden state is made, and so on. So one property here is that the newest hidden state always only depends on the previous hidden state, and it doesn't really directly depend on like the hidden state 2 before itself. It only depends on the hidden state right before itself and the input that corresponds to it. So this is the information flow. The other important property here is that these connections that make a hidden state into the next hidden state, and also that incorporate the input, they're always the same. So these functions here that incorporate the input, they're always the same in each time step. So the parameters are shared between them. And the same goes for the functions here that transform one hidden state into the next hidden state. Of course, there is a joint function between the two that actually produces the next hidden state. So these weights are all shared and for each time step, and that's what makes the network recurrent. So we call the single time step here, we call that a recurrent cell. And the question now is, how do you construct a recurrent cell? Usually recurrent neural networks, they run into this problem of either gradient explosion or vanishing gradients, because usually this here, if you are into neural networks, you know this, this is a weight matrix multiplied by the previous hidden state. And if you just multiply the same weight matrix over and over and over again, it pretty much depends on the singular value of that weight matrix. If the top singular value is higher than 1, then the signal is going to explode. And if it's lower than 1, the signal is going to fade over time. And there's pretty much nothing you can do. So classic RNNs have looked like this right here. So the next hidden state is a nonlinear function g, and g can be some nonlinearity like a sigmoid or a hyperbolic tangent. but it's a function of the current input and the last hidden state by simply matrix multiplying these two things by some weight matrices and then adding them up. So that's what we've just looked at. Now this is problematic, as I said, because of the vanishing or exploding gradients, and therefore people have come up with methods to solve this. And you might know things like LSTMs and GRUs that are used to solve this. Now these cells here are much more complicated than the standard cell that we saw here, but they also are much more effective because they don't have this vanishing or exploding gradient problems. Their promise is that they can remember things for longer because they allow the gradient to flow without these problems during backpropagation. Now, how does one of these look? In this paper, they mainly look at the GRU, the gated recurrent unit, which is a simpler version of the LSTM. The LSTM is slightly more complex, but the principles are the same. So they look at the GRU right here. What does the GRU do? These are the formulas for the GRU, and we're going to try to deconstruct these formulas. So as you can see, the inputs are the same. The inputs are going to be this point's input, this time step's input, and the last hidden state. Okay, those are all the quantities that we need, and we need to output somehow the next hidden state. Okay, the last hidden state is then used to predict the y, by the way, in all of these cases. So first we need to calculate two things called a z and r, and both of them are the same. They're multiplying these two things by weight matrices and then running them through a sigmoid nonlinearity. Okay, let's do that. Let's say we have the last hidden state here, and we have xt here. So first, we're going to calculate the zt and the rt from that. Now, every one of these arrows right here is a multiplication by a weight matrix. So every one of these arrows is transforming the input. And let's join this into a sigmoid node, and that gives you zt. And let's join these into a sigmoid that gives you rt. Okay, so far so good. Now we need to combine all of this in this last line right here. So you can see that the z thing here sort of acts as a switch. So z is the result of a sigmoid, and therefore it's between 0 and 1. And here, this is the Hadamard product. This is the element-wise product between vectors, which sort of means this is like a gating. This is like a switch. If it's 1, it selects this quantity, and if it's 0, it selects the quantity over here. And of course, it can be between 0 and 1, but those are the ends of the spectrum. So z is a switch that selects between the last hidden state. So let's draw that right here. So the last hidden state goes here and is one of the options of the output, right? So, and the option is given by z. So zt, how do we draw a switch? Like this maybe? So zt is responsible for modulating this switch right here. Okay, this gives you the next hidden state. You see, zt modulates that switch. So ht is the one possibility that the switch can select. What's the other possibility? The other possibility is this quantity right here, which is the hyperbolic tangent of whatever that is. So that is combined of x. So let's go from the back right here, tan h. What's the input to the tan h? It's two things. First of all, the x is an input to the tan h, so we can draw directly a line from here. The x modulated, every arrow, as you might remember, can be a function. Okay, not all arrows are functions. Like this arrow right here is not a function, it's just an arrow. Maybe that's confusing. You get what I mean. And the next thing is R times the last hidden state, or the last hidden state modulated by this matrix. So R is acting as another gate. R can be again between 0 and 1 because it's the result of a sigmoid. So this hidden state will also go here. It will be modulated, running out of colors here, it will be modulated by R here as a sort of gate. So R can either close or open this gate right here, and then that's fed into the tan H. So it's a rather complicated setup, as you can see right here. So let's analyze this. First of all, the hidden state is either the last hidden state or it is something new. And that's modulated by this Z right here. And Z is calculated from the hidden state and the current input, okay? So this allows the cell to basically look at the hidden state is sort of the information of what happened so far, and the current input is the new information that it gets from the sequence. And it sort of gets to look at these two things and decides, do I even want to update my hidden state? If not, I can just select this path right here, and then nothing happens to the hidden state. The next hidden state will be exactly the same as the last hidden state. If it decides, if it thinks, wow, this new thing in the sequence, that's actually important, I should remember that, right? Because remember, the task of the network sometimes is to remember things from the sequence. I think we drew this over here. So if this is an email and we want to detect whether it's spam, then this word in the sequence right here might be really important because it would say something like gold, like buy gold. These two things might be buy gold. And you need to remember that in the hidden state, because the only way that information from X is going to flow to Y is through the hidden states. So you would want, at this point, you would want to remember this input in the hidden state. So you'd actually want to update the hidden state. And then this here might be not as important. So you might want to say, I still want my hidden state to be the old hidden state. Okay, so Z is that gate that allows us to do this. If we decide to update the hidden state, then what do we do? Again, if we decide to update the hidden state, we will incorporate the new input, but we can also decide to mix that, how to mix that new input with the old hidden state, okay? So if we decide to update the hidden state, we don't simply discard the old hidden state, because the old hidden state will still have a path to the to be sort of still there, to be remembered. But it's a longer path, and it needs to go through this thing here and through this thing here. So this thing here decides which of the old hidden state pass through. So at each, you can see right here, this is an element-wise product. This R is going to be between 0 and 1 at each point in the vector. So at each point in the vector, the R decides, is this worth remembering or not? Okay. And if it's not worth remembering, then this is going to be 0, and that position of the old hidden state is going to be 0, and then that's going to be forgotten. And that's the opportunity for the hidden state to incorporate new information, because then there's it can delete this old information and then it can incorporate the new input, and that will result then on this path on the new hidden state. Okay, so there's two major things. First, we can decide whether or not to even incorporate new information. That's achieved by the Z gate. And then we can decide which parts of the old hidden state, if we want to update it, which parts to forget. That's the R gate. And how to update it is then basically a result of the weight matrix that's associated with this function right here. All right, so that's the gated recurrent unit. And it works a lot better than the classic RNNs. So having said that, they now turn to this property of neuronal bistability that happens in actual neurons. So this here is sort of a model of a neuron with this property. Now forget everything we said about GRUs. We're just going to look at this right now. what happens in a neuron usually is this is a single neuron. You have input synapses from other neurons. So these are connections coming from other neurons into you. They are accumulated right here. Usually they are just, in a classic model of a neuron, they're just summed up. You would sum up all these input signals, and then you decide, you'd run it through like a step function. So if the sum of all the things is smaller than a particular threshold, the output would be just nothing. And if it's higher than a particular threshold, then the output of the neuron would be sort of a firing of the neuron. This can be weighted and whatnot, but in this case, it's just a function of the inputs, and that gives you your input signal. So this is like, this is your input signal to the neuron. Now, there is this property right here that makes it interesting. The signal goes out here and is integrated. This is an integrator, and that's going to be in the output signal, but there's this connection, this back connection right here. And that means that the signal that comes out at time step t is going to be fed back into the signal and actually added to the signal before itself, and sort of self-modulating, right? The signal comes out, is sent back, is added to this input, and then sent through again. And this here is just an integrator that's integrating everything that's happening. So if you look a bit closer, you'll see that there is a minus here. So it's actually not added, it's subtracted. And there is an f here, which means that this is a nonlinear function. Now, if this weren't a nonlinear function, we can just sort of try, or let's say this is a monotonic function. We can just sort of try to estimate what happens. If all of this right here is very high, it's a high number, big number, this will be a big number. Then this sum will be a big number. This output will be a big number. What happens is this here will be a big number. This is monotonic, so it will also be a big number. And that means it will subtract that big number. So that means whenever the neuron is going to be very excited, this feedback would actually push it back. Now, when it is not very excited, so when it's a very low number, very negatively excited, then the feedback would work in the exact opposite direction. This will be very negative, this will be very negative, and this here would push it towards the positive. So this neuron somehow self-stabilizes over time to this, to the 0 point right here. And that's simply if this f is the identity function right now. So you can sort of see how this property works. Now, we'll make it a bit more complicated in that we'll assume that this f here is not the identity function, but let's say they have it somewhere, but this right here. So the f of v post is this here. It's v post minus alpha tan h of v post. Or is this the entire f? Yes, that's this thing right here. If this is the case, if this is the signal minus the tan h, then something very, very, very interesting happens. And that's depending on this alpha right here. In that if this alpha is between, if the alpha is between 0 and 1, then we simply have our monotonic function. So here you can see how big v post is, so how big the output signal is here. That's the experiment we made before. And here you can see what the feedback signal is, okay? Or the integrator, the integrated signal. Maybe this is in the wrong place, and maybe f is just minus the tan h. I'm not sure. But in any case, the way they build it after in the GRU, it's pretty explicit. So this is the thing we said before, namely if the signal is very high, then this signal here will be high as well. And because it's subtracted right here, it's going to push the signal back towards 0. Again, if this is lower than 0, then this thing here will also be lower than 0, and because it's subtracted, it's going to push the signal towards 0. So this thing here is the stable point. It will always push it back towards 0. However, if we change the function and we change just the parameter alpha to be 1.5, a very different thing happens that you can see right here. Then it turns out if your output signal is very high, the same thing happens. It's going to be pushed back. But if your output signal is between 0 and this point right here, there is a regime where actually, even though the output signal is positive, you will be pushed towards this point right here. And therefore, there are these two stable points right now. And the stable point basically means if the signal deviates from it, it's going to be pushed back towards that point. And you can see these two stable points, they're not at 0. They're actually at these 2 points here. And that's pretty interesting because that means you can potentially remember things with the cell, right? An output signal of 0 is basically not informative. But here you can be in either the state here or in the state here. And the little perturbations will still keep you in that state. So you could potentially be in this state right here as an output, and the cell will just keep updating itself and be stable and always output that signal right here. And then you could go ahead and if you then provide some huge input signal right here, you could potentially throw this over to the other side, over this hill, and then it would stabilize at this point. So this is sort of a way to remember things within these biological cells. Pretty cool. Now this here is a non-filled out circle. That means it's an unstable point. It's technically stable in the sense that if you're exactly at 0, you will remain at 0. But if you perturb even a little bit, you will go. If you perturb a bit, you will go away from it. Okay. I hope this sort of property is clear and why this is so fascinating, because we can use this fact that the stable points are not at 0 and are more than just one stable point for remembering things. And they're now trying to fill this into the gated recurrent unit. So they call this the bistable recurrent cell, BRC. And the formulas are these right here. Maybe a little smaller. Come on, I can't zoom anymore. Okay, now. It looks almost the same as the GRU. So the formulas are these, this, and this. So let's analyze the differences to the GRU. The first most striking difference is that a lot of weight matrices here have become single numbers. Or single vectors. This here used to be a weight matrix, and this used to be a matrix multiplication. And you'll see this sort of throughout. Whenever the last hidden state is incorporated into these things, then you'll see that it is no longer a weight matrix, but is in fact a product with a vector, a element-wise product. And that has a reason. Namely, what they want to model is individual neurons. So on a biological level, a neuron can only feed back onto itself. If there is a layer of neurons right here, they can only each feed back onto themselves. Whereas in a recurrent neural network, my hidden state is a vector. And if I transform this into the next hidden state, or any quantity, let's say I transform this H into this R right here, right? And this R is a vector too. Then any interaction is possible. So any cell, any entry in the vector here can influence any other vector because there's a big weight matrix in the middle. Okay. They want to leave this away. They want to model this as close as possible to actual layers of neurons. And therefore they say, okay, the input X can, be distributed to all the neurons because technically the input comes from some other neurons down here, and they can all have connections to these neurons, but these feedbacks, we only really observe them in individual neuron, this feedback cycle. So that's why they model these recurrent weight products by just element-wise products with vectors. And then the second difference, you again see that there is this switch right here, this C switch. And the C switch is, like before, it's a sigmoid where combine the output and the previous hidden state. There's nothing new here. So this switch is the same. The cell has the possibility of letting in new information or just ignoring the new current information, the XT. The second thing is here. And this is the same as well, right? The tan H, this is a combination of the new information. It's in case we want to let in the new information, of the new information, and you need to decide what things of the old information to forget or remember. Now, the difference here is in this A. So this A used to be, again, this sigmoid of the combination, and now it's just slightly different. It used to be sigmoid. Now it's 1 plus tan H. This is a very, very slight modification. It's tan H because tan H is between -1 and 1 instead of 0 and 1 like the sigmoid, and the 1 plus makes it such that this is between 0 and 2. And we've seen before that this critical behavior, there's two regimes to these functions. When it's between 0 and 1, this behaves like a classic gated recurrent unit, like a classic GRU. But when it's between 1 and 2, then you have that exact behavior that we saw before of the bistability. Okay, so depending on what the A is, if the A is 0 to 1, it's a classic cell, and if the A is 1 to 2, it's a bistable cell. And the network can decide by itself what it wants to do, because here it can actually learn how to do that. All right, so this is the only change. The only change really, apart from it only being individual neurons feeding back on themselves, is that now this is no longer between 0 and 1 with the sigmoid. This is now between 0 and 2 because it's 1 plus the tan H. Very simple change, but the effect of this is pretty cool. So they do some, here is like a schematic drawing of this. If this A is between 0 and 1, again, you have this stable state that's at 0. But if it's between 1 and 2, you have two stable states at two non-zero points. And again, this, we already saw this, but now this is for, I believe, this recurrent cell, this bimodal recurrent cell, not for the neuron itself. And here they give an example of what happens when you run this particular signal, this particular time series, through a cell like this while fixing the C and the A parameters. So now the C and the A parameters aren't learned, they're just fixed, and you see what happens. Now, as you can see, the blue should be a classic, the classic behavior. So in this blue case, what happens? You see right here, this C is moderately low. So we saw that C is the switch of whether to leave in old information or take up new information. If it's low, it means we want to take up new information. This is reasonably low, and that's why when the signal goes up here, the blue line goes up as well. And when the signal goes down, the blue line goes down again, and so on. So the blue line pretty straightforwardly follows the signal right here. Okay. Now, in contrast to this, the red line is over this threshold. So A is fixed at 1.5. C is still at 0.2. So again, when this line goes up, then this line goes up. But because this is near this stable point, if it goes down again, it doesn't appear to go down enough. It sort of remembers that state it was in. It doesn't go down with the signal. Only now that it goes down even further, it's over this threshold. So we were in this situation now, And the first bump down was only like to here, and that pushed it up again. But now it jumps over here because the signal is even lower, and then the cell sort of switches to another state. As you can see here, it goes down. But then this bump here is not enough to bring it up again, so it kind of remains in this state. So you can see it sort of remembers the input, and small deviations or small changes in signal don't manage to throw it away from that. Only larger things. Only it needs to go the signal needs to go very much down in order for it to change state. So that's pretty cool that there's this remembering behavior. And now remember, in the actual implementation, these C and A parameters, this C and this A right here, aren't fixed. They are also determined by the cell itself. And therefore, the cell can decide by itself when it wants to remember things, how hard it wants to remember things, and so on. So we're going to check this out in an actual implementation. So there's this one last modification they make where they say, okay, they tried this and it doesn't really work because, so it works sometimes, but there is this issue of these neurons connecting only back on themselves, which really makes the model much less powerful than a classic recurrent cell. It's closer to biology, but it's much less powerful. And there is this property, they say, of neuromodulation, where technically in real neurons, the one neuron here could influence another neuron by modulating these A and C parameters. Okay, these A and C parameters, this is called neuromodulation. So there are interconnections between the neurons that influence how much other neurons remember and forget things. So they decide, let's model that, and lo and behold, we're now back to having weight matrices right here. So this is sort of, they say this is not really a super biologically plausible way of implementing neuromodulation, but it's an easier way, and it brings us closer to back to the GRU. And yeah, so now the only difference to the GRU is that the fact that here there was a sigmoid, now it's a 1 plus tan H. Okay? I find this pretty cool. So now also the only difference here is this property of bistability. This is the only difference. And now we can actually compare. So let's compare. They first they do these sort of benchmarks, which they're pretty neat. So they have this first benchmark where it's the copy first input benchmark. I'm having some trouble here moving this paper around with my fingers. So the copy first input benchmark is simply a time series. In this benchmark, the network is presented with a one-dimensional time series of t time steps, and each entry is a random number. After receiving the last time step, the network output value should approximate the very, very first input step. Okay, so all the network needs to do is remember the first thing it sees. And that should be learnable, right? That should be learnable because it's not specified whether the 0th hidden state, the initial hidden state, is given into the network, but technically it doesn't matter because it can just learn whatever that is. It can learn to have a designated bit in this hidden state. So this hidden state is of size 100, I believe. One designated bit in the hidden state of whether it has already encountered the first thing or not. If it has not encountered, it means that it's at the first time step. Therefore, it should incorporate the new information into the hidden state and also set this bit. And then for each subsequent step, it can see I've already set this bit, and it can simply close that gate. That makes it incorporate new information. So it should be able to carry this information all the way to the end by simply always closing that gate after the first step. And what happens in this, so as you can see, when the result is up here. So this is after so they train it for 300,000 gradient descent iterations. And you can see that when these time steps, when the series are pretty small, the LSTMs or the GRUs tend to perform well. But you can see that these BRCs, they don't tend to perform poorly, they're just performing worse, right? It's still the 0.01 regime or something like this of error. However, when you go up to like 300 steps, then you can see the GRUs and the LSTMs, they start to fail because they are not made explicitly to remember for that long. They don't have this bistability property. Whereas now these things excel. You can see they're still pretty low. And at 600 steps, these things completely fail. They completely forget the input. So, and the NBRC at least is still able to remember the first thing pretty well. And yeah, so the second one is, no, this is the first experiment, still the copy input benchmark. You can see right here that even at this 100 thing where the GRU still learns it learns it much later than the BRC, which learns it pretty fast. Only here, when the series are only 5 steps long, does the GRU slightly outperform the BRC. So the general notion here is that these classic cells are more powerful in like classic tasks, whereas these things are shining whenever these things fail because they can't remember things for very long. So they're not, these new cells are not state of the art yet. Possibly there are still some modifications to be made. We've had a pretty long history of optimizing GRUs and LSTMs. They haven't always worked so well as they do now. Because we kind of know how to handle them. And I expect if these cells here take off, especially these NBRC, then with time we'll be as proficient at handling them, and they will probably become on par or even outperform the LSTMs or GRUs on everyday, like on all the tasks, and then be especially good on tasks where you have to remember things. But for now, they're outperformed by LSTMs and GRUs. Okay, so the second thing is a more interesting experiment, the denoising benchmark, where they say the copy input benchmark is interesting as a means to highlight the memorization capacity of the recurrent neural network, but it does not tackle its ability to successfully exploit complex relationships between different elements of the input signal to predict the output. So they have a new benchmark. In the denoising benchmark, the network is presented with a 2-dimensional time series of t time steps. 5 different time steps are sampled uniformly with and are communicated to the network. Okay, I'll just tell you what's going on. So this new time series is 2-dimensional. In the lower dimension, you simply have a bunch of random numbers like 5, 8, 2, 9. Actually, these are numbers sampled from a uniform Gaussian or so they're not actually 5, 8, 2, and 9, but you can imagine it like this: 5, 8, 2, 9, 3, 4, 0, 2, and so on. And in the second dimension, you have a -1, I believe, almost anywhere, and then at some points you have a 1. So you have a -1 again, and then you have a 1, and a -1 again, and at the last point of the sequence, you'll have a 0. And so the 0 is simply a marker that it's the end of the sequence. What the network needs to do is it needs to output all the elements. So the output of the network should be, in this case, should be 9, 4. So all the elements where there was a 1 in order. Okay. So remember what it needs to learn. It needs to learn to, every time it sees a 1 in the second dimension, it needs to take the first dimension, put it somehow into the hidden state, and then carry that hidden state forward. And it sees a 1 again, it needs to take the second thing, also put it into the hidden state, but not override the first thing it put into the hidden state. Like if it were to just realize, I need to put this into the hidden state, then it would almost surely override the previous information. So it needs to be able to say, I've already kind of so my H is going to be a vector of 100 dimensions. It needs to be able to say, well, I've already stored a bunch of stuff in that part of the vector. Maybe I should store that thing here over here. So this is fairly complex things to remember, and technically GRUs and LSTMs are able to do it, but as we'll see, they're not as much. The results are in this table, where you can clearly see that whenever the n, so the n is a parameter that is how far in this direction are these ones. So when n is 0, the ones can be anywhere. But when n here is like 5, that means that the last 5 ones surely don't contain a 1. That means only the first, whatever, L minus 5 contain the 1. So the higher this number n is, the harder the task, because your learning signal is way farther away from when you get the output. So you can see when the n is low, then the GRUs and the LSTMs, they perform pretty well. But also these cells perform pretty well. They're just not performing as well. However, when the task gets harder and you actually need to learn a sparse signal over a long period of time where in between you don't get any signal, the GRUs and the LSTMs fail, while the BRCs would still be able to learn these kinds of things. So that's fairly cool. Now, if from a researcher's perspective, I wonder if they just first tried this task, as I described it, and then they discovered like, crap, they can still do it. And like, okay, how can we make it such that there's a difference? Okay, let's actually make the task harder like this. And then they did that. I wonder if they always had the idea with the n here, or just introduced this after they failed to produce a difference in the first place. I'm not sure. But they have another benchmark, but they basically show that these cells are actually good, can incorporate this information, can reason about what they need to remember and what not. And in the end, they also have this sequential MNIST, where they just feed an MNIST digit by digit. And at the end, I think the output of the neural network needs to be the class of the MNIST digit. And again here they have a parameter called n black, which means that, so they have an MNIST digit, it's like a 3, they unroll it to a single vector, right? They feed this one by one into the recurrent network, and then after that they attach a certain number of just empty pixels, black pixels, and after that the network needs to predict the y. You can see if they ask the network the class of the digit immediately after it's done, then the GRUs and the LSTM perform fairly well, as do the BRCs. But if you attach a whole bunch of these black pixels, remember an MNIST digit has some 784 maybe entries. So attaching 300 black pixels is quite significant in terms of the length of these sequences. And then the GRUs and the LSTMs, they can't learn to ignore these things because the learning signal is just too far away right here. But these things, they can, because they can exploit this bistability property and remember things. Again, I wonder how this came to be. Seems pretty funny. But the last thing they do is they investigate what happens in their cells. And this, I feel, is the most interesting part. And they do this on this denoising benchmark, so the task we've looked at before, where you need to remember 5 randomly selected numbers that are indicated by the second dimension. Here they show a sequence where the 5 numbers occur at 30, 100, 246, at 300, and at 376. So these are the 5 positions where the sequence indicates that the network should remember the thing in the first dimension and then output. They analyze 2 things. They analyze the proportion of bistable neurons. So basically they analyze these A quantities, and they analyze how many of the neurons in the layer have an A that's higher than 1, which means that they are in this bistable mode. And also they analyze what's the average value of C. So C, if you remember, if this is high, it means it doesn't let in new information, and if this is low, it means it lets in new information. Now, if we first look at the C, you can see that every single time when the second dimension indicates that this is one of the inputs to remember, the network immediately drops the C values. The different colors here are different layers. The recurrent network has multiple layers of these cells, as is usual in the recurrent neural networks. So this C, as you can see, it goes up pretty quickly, and then as soon as one of these inputs appear, the C drops, which basically means that the network realizes it now must let in the new information, and then it immediately shoots back up. Makes it seem like, so the network says, oh, okay, as long as, so all of these inputs here, they have the -1 in the second dimension, right? So it recognizes and it says there's no reason for me to incorporate that information. It's not important. And as soon as the second input comes, it immediately shoots down again. Now you can see this here is the last layer of the network, the highest layer. So sort of the highest abstractive information. And you can see that from input to input, this value of C gets higher and higher, and these spikes as they go down, but they go down to a higher and higher point, which is the fact that it recognizes it needs to let in new information, but it lets in less and less new information the more things it needs to remember. So not only does it recognize, wait, I need to remember this, it also recognizes, but I probably shouldn't completely forget what I had previously, because it is important for me to remember these previous things. So that's a pretty cool demonstration, the fact that these go down at the input and the fact that generally they go up every time after a new input is incorporated into the hidden state. This shows that this is a pretty good indication that what they're saying is really happening, right? Okay, the second thing shows almost the same. It shows how many of these neurons are actually in their bistable mode. And you can also see right here that, especially in the last layer, you can see that the number of neurons in the bistable mode goes up and up and up and up after each of these steps. And these spikes here correspond to always the points where they have to let in new information. Okay? Cool. So I find this to be pretty cool, and I find this last experiment to be the coolest, where they can actually show, look here, there's a pretty good indication that the thing we built does what we say it does. They also actually have a proof here of the bistability when this A is higher than 1. I won't go through this right here, but if you want, you can look at that. I'm excited to see what happens with these kinds of architectures in the future, because it seems to be a pretty minor modification, and maybe with a little bit of more modification, or if we sort of just tune this a little bit and kind of figure out what we have to do to make these things actually compete with the classic GRUs and LSTMs in regimes where a long memory isn't necessary, I feel this could be a, kind of a standard building block in the recurrent neural network toolkit, even though it's been sort of outperformed by transformers in previous years. All right, that was it for me, and I hope you had fun with this paper. I invite you to check it out, and bye-bye.